and get the current slide up here. And for some reason, it's not acknowledging. Help any? No signal. Let me try something here. There we go. Did that do it? I think it did. Probably. Made it so my cord is not connected. They are running in tandem today, trying to... Okay, now for the moment they're both working. So hopefully they will. Okay. The only announcement I know about today, major one anyway, let me say this too. This has been happening for the last several weeks. I'm in the process. We've got so many things going on. Been trying to get my annual evaluations wrapped up. I'm within 2 of getting those complete. And we're in the process of preparing for our, what they call planning hearings, which are coming up next week. And so therefore, most Tuesdays and Thursdays I've not been and I won't be available from 10:45 until 4:30 is what is listed on the syllabus and my locator cards and stuff, because I've been having to go to the Birmingham campus to get evaluations signed or to gather materials for the planning hearings and all that kind of stuff. That's going to continue this week. Today I've got at least one evaluation. He's supposed to be there today, so I'll probably be leaving somewhere around 2 o'clock to go over there. And on Thursday, we've got a meeting around 2 o'clock, so I'll be over there. 2:30, so I'll be leaving to go over about 2 o'clock then. The following Tuesday is when we actually have the hearings, and therefore I'll be over there again on Tuesday. After that, knock on wood, we're going to go back to my regular schedule, okay? But we're almost out of term. So please, folks, get your stuff in. And this class has been pretty good about that, except for research papers. 2 out of my biggest class, 2 research papers in. But everyone's turned in the first test, and almost everybody has turned in the second test. I think I got one today, and that means I'm still missing one. Okay. So, anyway, has everyone done the student course evaluations? Okay, a few people have. If you haven't, you do have till the end of the term, but please don't forget about them. Okay, please do your student course evaluation. Pretty easy. How long did it take?
They said about 30 minutes.
30 minutes?
Yeah, I don't know what they talking about.
Okay. Let me see if you can say that with a straight face.
I can do that.
All right. Okay. Any questions on what we've done so far? Okay. Any questions on what we've done so far? We're in Chapter 4, which is integration. We're in 4.2, which is talking about area of a plane region. And we are, example 3A is approximating the area of a plane region. Okay? Now this, frankly, gets, to me, in my mind, tedious. Okay? Hang in there, wade through it. After a while, we'll find a much quicker, shorter, more direct way, and I won't say you can forget about this way, but it can be a thing that you said, well, at least that's over with. Okay. So here, I think we need to go back. I don't know why it left. Okay. should have been here, area of a plane region, and this is where we should have been. Somehow it bumped up. Recall from section 1.1, okay, that the use of rectangles, as we say here, to find the approximations of the area of a region lying between the graph of alpha of x equal minus x squared plus 5 and the x-axis between 0 and 2, which is the same as 10/5, okay, you can use this area of rectangles, okay? Now, if you inscribe the rectangles so that you're using your x of 1, x of 2, x of 3, x of 4, x of 5 to define those points, okay, then this is going to underestimate the area of that curve, under the curve. But if you use the superscribed rectangles, you're using the left endpoints, 0, 2/5 for this one, 4/5 for that one, 6/5 for that one, 8/5 for that one, and 10, not using 10/5 here. You're using the superscribed rectangles with the left endpoints. This is the right endpoint. And now you're overestimating the area under that curve. So one thing you could do was using this thing under and over. Boy, that board is in awful shape, isn't it? Other people use the room, and I think must have used it last Thursday since we were last in here. Hold on a minute, I want to see if I can clean that door a little bit. That's awful. It's been sort of murky, but boy, this has gotten worse. The whole board needs to be cleaned, but I'm just going to try to get this that we've been using. I have to hit it again. I was over on the farm in Georgia this weekend and doing a lot of mowing and other things like that. So I'm so stiff and sore. I have to swap arms every now and then, aching everywhere. Is that a little bit better? Okay. So here are two approximations. I was going to say, if you were to take this approximation, add it to that one, and take the average, you're going to come out really close, because you see this overestimate here is pretty close to the underestimate here. This underestimate here pretty close to the overestimate there. Because this is a pretty regular curve here, you would do a pretty good job of coming close. Now, that's not what we're going to do, but that would be a way to do a little bit better, okay, than just using either one of these. All right. Now, using the right endpoints. Oops, wrong way. Okay, the right endpoints, this one here. The right endpoints of those rectangles. then what's the area of the rectangles approximating the area of the parabolic region? Well, this rectangle would be f of 2/5, so all we do is plug 2/5 in here, square it. That would be 4/25, but it's negative that. So 5 minus 4/25, you have to figure out what that sum is. Then do the same for this one and that one and that one and that one. Okay? Add those up, and that's your estimate of the increment. Okay? If you were to do these, you're using the left endpoint, so your first estimate would be 0 here, which would be 5. Okay? And then this would be the same estimate you had here, that's the same estimate there, there's the same estimate there, there's the same estimate there, and rather than using this estimate here, that would be the last one we did, because that would cover that. Now, and then you add those up. Now, let's break it down, not doing it quite as literally as I just said. Let's break it down into sort of using your little eyes there. Remember, we did these last week. Your eyes here are your which increment you've got. And in both cases, you got 5. Okay? Here, 1, 2, 3, 4, and 5. In this case, 1, 2, 3, 4, and 5, because we don't use this one here. We don't use this one here. So in both cases, 5. So your increment, you have i's equal to 5. Okay? Up to 5. It's a counter. The width of each rectangle, okay, is 2/5. 2/5 between this one, that one, that one, that one, and that one, all the way across. Okay, so your delta x is 2/5. Okay, 2/5, and your value of those integrals will be 2/5 times I. See, 2/5 times 1 would be 2/5. 2/5 times 2. I is counting 1, 2, 3, 4, 5. 2 times 2/5 would be 4/5. 2 times 3/5 would be 3 times 2/5 would be 6/5. 4 times 2/5 this, and 5 times 2/5 that. Okay, so that's tells you where the right endpoints are. Okay, that tells you the value of them. 2/5 I, where I is a counter from 1 to 5. Okay. The width of these, each, as I just said, was 2/5. The height is the f at these values. So f of 0, that doesn't look right. Okay. Oh, these are the intervals. Okay. I was going to say these are not ordered pairs, but these are not. These are brackets here. I was seeing parentheses. This is the evaluate the area of this interval from 0 to 2/5, from 2/5 to 4/5, 4/5 to 6/5, 6/5 to 8/5, and 8/5 to 10/5. Okay? And we're going to use the right endpoint to evaluate each of those intervals. Okay? I mean the height at each one. So we're going to plug that in here. All right. The sum of the areas of the 5 rectangles. The height is f at 2/5 I, where I is a counter from 1 to 5. Okay? So your f is going to be evaluating this on the right endpoints. 1, 2, 3, 4, 5. Okay? Of those. And your width is always 2/5. So you can, they pulled the 2/5 out here. I would have pulled it out front, okay, because that's a constant. And then you're evaluating the summation from I is equal to 1 to 5 of minus 2i over 5 squared plus 5. Okay, remember that was your equation, minus x squared plus 5. That was the value, the height, the y value. You multiply that by 2/5, so I would have put this here. And they just bing say it's 162 over 25, okay? Without telling you really how they did that. Now, it's not really very fair of them to do, is it? Pull this out, and then you're evaluating this just like we did before. Remember, we could again pull out the 2/5 in front of. It's remember our summation formulas from on page 259. Okay, I'll go back and let you see those. Here they are. Okay, the I squared, I squared, I cubed, and the constant. Okay, remember those. We'll come back to them if we need them. Okay, don't memorize them, but you know. So we're doing example 3, which is quite a ways over here now. Boy, they just jumped the gun on that and said, this is what they are. Okay? Now, we hadn't already done that earlier, had we? I don't think so. So, I don't see how they got away with it, but they did. Okay. All right. So, let me get my pen set up. There we go. All right. So, first pull out the 2/5 here. And then that'll be the summation I equal 1 to 5 of minus 2I over 5 squared plus 5. Now I'm doing it in gory detail here. Okay? Now, pull out, okay, 2/5, don't lose that. Don't forget it. Okay? Now, what we're going to do is pull out the minus sign and the 2/5 squared, because that's not really entering the picture here. So this will be times a minus 2/5 squared, which I could have just written as minus 4/25. I should have, but show you how we got it. Now do the summation, I equal 1 to 5, and what do you have left? The I squared. Okay? Plus, now here we split the integral here. I mean, not integral, the summation. I equal 1, let's bring the 5 outside, 1 to 5 of 1. Okay. So it's a 2/5 here. Don't forget that one. Get out of there. Okay. And then this one I'll go on and do, like I said before, minus 4 over 25. Okay? That's going to be out there. I don't really need the parentheses, do I? Okay? Now, I said remember, okay? Let's go back and get what the summation of I is equal 1 to 5 of I squared is. Okay? Anyone remember what that one was? I'd say just turn on the book, but not all of you have books maybe. Okay, I squared is n times n plus 1 plus 2 times 2n plus 1 all over 6. And this is I is going from 1 to n. Our n is 5, so it's going to be 5 times 6 times 11 divided by 6. Okay, so let's go back and do that. All right, so this is going to be, another parentheses here, 5 times 6 times 11 times all over 6. Well, the 6's are going to cancel out. Okay, plus 5. Now, what do we have here? I equal 1 to 5, 1. That's 1 plus 1 plus 1 plus 1 plus 1. What does that add to? 5, yeah, very good. All right, 5 times 5. Okay? Now, that would be a 2/5 times a negative 4/25 times and that's just in front of this one. 5 times 11 is 55, okay, plus 25, okay. Make life a little bit easier here. 5 will go into 25 5 times, 5 will go into 55 11 times. So this will be 2/5. That's a pretty ugly 5, isn't it? Times a minus 44/5 plus 25. Okay? Well, in order to do the math here, let's make this 125 over 5. Wouldn't you say that's a good idea? And then 44 from 125, that'll be 2/5. I believe that's going to be 81, isn't it? 81/5. Okay, if I haven't made a really stupid math error here, I think that comes out 162 over 25. That's where they got it. 162 over 25. And then you can divide that on your calculator, and you get an estimate of about 6.5. Okay? Now, that's an estimate. Of course it's an estimate. It's an underestimate. We know that because here is what we're calculating. We're calculating the purples here using the formulas we just had, those little rectangles. You know that's underestimating. So 6.5 is well underestimating that. Okay? Is this making sense? Okay, what's that?
Summation of what?
I can't hear you.
The theory. Summation of what?
One more time.
Integration.
Integration. Okay, it's chapter 4, integration, 4.2 area. It's example 3 on page 261. Is that what you're asking? Is that what you're asking or something else?
I'm asking what the theory is called. It's called the summation.
I'm sorry?
I said the theory is called the summation.
Yeah, this is sigma notation is what they call this, is what it's under, and it's finding the area using sigma notation and using those little I rules that we had back a couple pages back. They just said, here's what it is, that's what it comes out being, without showing you how they got it, okay? Which, to me, I mean, what you could have done was count each one and do, this will be minus 2/5 squared, which, plus 5 times 2/5 plus blah, blah, blah. You could do them each at a time, and that is pretty time consuming. Or using your method of the I values, and that takes away some of that grunt work. But it's still a lot of grunt work, okay? Now, if you did it the other way, okay, I think I'm going to erase what I've got here. Oh, wait, okay. And there's a real big part of me that says, don't sweat this too much because we're going to find the easier way, okay? This is leading to how we do it more easily, okay? You got it? All right. So let me erase this. Okay. Because each of the 5 rectangles lies inside the parabolic region, you can conclude that the area of the parabolic region is greater than 6.5. Okay? 6.48. Okay. Now the left-hand endpoints of the 5 intervals are the left endpoints. Now let me go back and do those. Okay? The left one. We did the right ones here. Let's do the left ones now. Now remember our I sums and things like this we were using? They always started with n equal 1. So if you're using the left one, that looks like you're going to start with n equals 0. So what they do is I minus 1. And that way you can still start your sums with I equal 1, but 1 minus 0, 1 minus 0 1 minus 1 would give you 0. So that way you're starting at these values, not doing the last one. Okay? So that's why, there it is. That's why for the left endpoints, not the right one, but the left one, we do the 5 intervals are, here are the endpoints, and to have it I equal 1, 2, 3, 4, 5, you do 2/5 times I minus 1. The I minus 1 takes you back to, this becomes a 0, 1, 2, 3, 4. And that gives you the left endpoints, okay? And this would be the thing that you calculate now, okay? The width of each rectangle is still 2/5, so you would have it here. I would have pulled it out front. They put it at the end, which makes it a little weirder looking because you think you have to multiply everything by that. You don't. You can pull it out here and multiply it at the end. But this time, these are the endpoints, 2/5 I minus 1. So it's 2/5 I minus 2/5, okay? Which would be this, and that's what your function is. And that's where you do this minus this squared plus 5, okay? Still got the 2/5, it's going to come here. Now, this time you've got a bit more to do here. You've got to square the binomial. That'll be 4i squared minus 4i plus 4. Actually, I wouldn't have done that. I would have pulled the 2 out. In fact, pull the 2/5 out front of this one, okay? And then just had I minus 1 here. That would have saved a lot of effort here. But they don't show the effort anyway, so they're just doing, and they, lo and behold, here's what the answer is. Now, do you want to see that worked out just like we did last time, or you think you can follow the process? I'll be glad. Say again? Which? I can't hear you.
Let's just write it out.
Write it out. Okay. All right. So, let me get some white space to do that. Okay. Let's do it here. All right. I'm going to jump down here and copy what they have here with a little bit of an exception here. Okay? First thing I'm going to do is pull the 2/5 out front. 2/5. You might be required to do a left or right endpoint, but this is a rather awkward example, okay? But, okay. Follow the process here. Don't get too bogged down in the details, but follow the process, okay? So the 2/5 is out front, so I'm going to pull that out in front of here. Then I'm going to put the summation sign, okay? We're doing I equal 1 to 5, just like we did before. And I'm going to jump to this next thing here. Let's just imagine this 2/5 is out front. I should have drawn it here, okay? Now, before I do the other thing, notice here is what you're counting, okay? It's 2/5 times I. Rather than multiply it out here, keep the 2/5 on the outside and just have an I, okay? So in front of this, I'm going to pull out the minus 2/5, okay? Minus 2/5 squared, which again is going to be 425 squared, not 4th power, okay? Let me clean that up just a little bit. Okay. It just sort of irritates me that they put all this in and just say, here's the answer, you know, and don't tell you how they got there. Okay, so what we've got here then, I pulled out the minus 2/5 in front of the squared, minus 2/5 squared, and what we've got left is an that was basically this thing squared. So what we got left is a I minus 1 squared plus 5. But let's go on and put, well, I'm skipping a few steps here because it's hopefully should be pretty clear from what we did last time. 5 times the summation I equal 1 to 5, okay, of 1 then, okay. Now this is the same thing up here that we have here, if you look at it. Except I've moved the 2/5 out front, and then all the thing here is inside the bracket, okay? Now, I also pulled a minus 2/5 squared out in front of this summation sign, okay? Because I'm doing the summation here and the summation here. So just doing this one, pull the minus 2/5 squared out there. Now notice the minus is outside the parentheses, so the 2/5 is squared separately, okay? So what we have left here is just the I minus 1 squared. That's the first sum. Plus 5 times the sum, I equal 1 of 1. You could leave the 5 in there if you wanted to. I don't care. It's probably a little easier to do, but it's so easy to see it this way. All right. So that's exactly what we've got here. Just written in different form. Pulling the 2/5 out here. This 2/5 just in front of that sign, and the 5 in front of its sign. Okay.
Also, in the bottom it says 2.
I'm sorry?
In the bottom it says 2I.
Yeah, I know. I pulled the 2/5. See, I factored out the 2/5 out of this, leaving just I minus 1. Right? Pulling out the 2/5, and that's that 2/5. In fact, there's the minus sign in front of it. Now, this 2/5 is this one out here. Just too many 2/5 here, but yeah, you see, that is the same. All right. So let me. Oh, this is going to be hard to do. No, it won't. Okay. I thought it was going to erase what I just wrote. Okay. All right. Now, we're going to do the math, okay? The 2/5 up front, bracket, the minus 2/5 squared is going to be minus 4/25, just like before, if you remember. Now, this time, we have a summation of I equal 1 to 5, okay? And let's expand that binomial. Square the binomial. What would that be? I squared. Just expand that binomial. Minus 2I plus 1, right? Plus 5 times that last one. I equal 1 to 5 of 1. Okay. All right. Now we got 2/5 times minus 4/25. I'm going to break out again. Now I need another grouping symbol here. I should have done it up the other way. Okay. This time it's going to be the summation I equal 1 to 5 of I squared. And then we're going to have a minus 2 times the summation I equal 1 to 5 of I plus the summation I equal 1 to 5 of 1. Plus, whoops, that should be the brace. Okay. Plus 5 times the sum of I equal 1 to 5 of 1. And that closes that. Okay. What I did, we expanded this here, and then I broke that into the pieces. Okay? Summation of I, that's an I squared. I don't know what happened to the 2. Okay. That was weird. Okay. Summation of this minus 2 times the summation of I plus the summation of 1, and then we have this one out here. Okay? Now we go back a couple of pages, And let's write this in. 2/5 times minus 4/25 brace. Okay? Rather than flip on the thing, I'm just turning in my book. The summation of I squared, just like we had before, was n times n plus 1 times 2n plus 1 over 6. Just like we did before, the n is 5. 5 times 6 times 11 over 6. So that's 5 times 6 times 11 over 6, and the 6's go out. That's supposed to be an 11 there. It's pretty ugly. Same as we had before, okay? But what we didn't have before was this one, minus 2 times the summation of I. Now, if you go back a page, the summation of I is n times n plus 1 over 2. That was good old Gauss's or Euler or whoever it was that he did when he was in grammar school, n times n plus 1 over 2. So that's 5 times 6 divided by 2. So it's 2 times 5 times 6 divided by 2, and 2 will go into 6. Well, actually, let's leave the 6 there. Just cancel out the 2 here. That would be easier. Okay. Plus, and what is 1 plus 1 plus 1 plus 1 plus 1? 5. That's your 5 again here. But this time it's inside the brace here, and this one is outside the brace here. 5 times 5. Okay, just like we had before. All right. Now, since I've run out of room at the bottom, let me erase that at the very top up there. And we'll put in our answer there. Okay. I'll erase that too. Not that it mattered any. So here we have a 2/5, that's that one, times, big bracket, a minus 4/25, okay, times a brace, and this came out being 55, okay, minus 30, plus 5, that's all in the brace, plus 25 inside the bracket. All right. I have a feeling I've left off a term somewhere, and I just can't see where I did that. So if this comes out wrong, there is someplace I've made a dumb mistake. And I may not have, but it just doesn't feel like it's the same ballpark as the other one, but I may be wrong. So let's see what we got. Okay. So that's 2/5 times a minus 4/25 times, I'm going to put it in parentheses this time, that 60 minus 30 is 30, right? That's all of that, and then plus 25. Okay, well, 5 will go into this 5 times, 5 will go into that 6 times. So that would be, I probably need to erase another line. Sorry, if you got paper, you got more room than I do. You don't have to erase these things. You can leave them there so you can go back and follow it. I sure hope I haven't left off a term somewhere. Has anyone seen one missing somewhere? Because I'm erasing all my original material, so I won't have it. That's a 2/5 times a minus 24/5 plus, and if you put that over 5, that would be a 125/5 fifths. Okay, so this will be a 2 fifths times a, pretty sure that comes up to being a 101 over 5, which I think comes up being a 202 over 25. Now, is that what they got? Let's see. Yep. Let me erase this down here. Probably should just erase it all. I want you to see mine and that at the same place. They just magically said that's 202 25ths. Okay, that's how we got it, right up here. Okay, 202 25ths. Okay, again they just left off scads of steps, and that comes up 808. Okay. For some reason I'm going to put a 5 down there. I don't know why a 5. Does anyone else come in since it's all right? Okay. So, that's how they got their B part. The A part was the 6.45, 6.48. The B part was 8.08. By combining the results, you concluded somewhere in between the two. Frankly, I would average the two, okay? That would be 14.56 divided by 2 would be 7.28, okay? Hang on to that one, 7.28, okay? Now, what they're going to do now is, let me go backwards. What happens if you increase the number of rectangles? Rather than having it being 2 fifths, make it 1 fifth. So you have 1 fifth, 2 fifths, 3 fifths, 4 fifths, 5 fifths, 6 fifths, 7 fifths, 8 fifths, 9 fifths, 10 fifths. Well, then your rectangle here would be a smaller error. One here would be 2 smaller errors. This will be 2 smaller errors, 2 smaller errors. Or over here the same way, and you get a better estimate. Okay? And they suggest those come out rather than the previous one. When you use 2 fifths as your interval, okay, using 2 fifths as the interval, you now have 6.48 is less than your area, is less than 8.08, and they don't do the math, they just tell you to do. By changing it to, this time they said, don't just do 10 rectangles, let's do 25 rectangles. Then that comes up to be 7.1712 for the interior ones. That's less than your area, and that's less than 7.4912. I can't write. 7.4912. That would be the area then. So you see now you've zoomed in even greater, and you have a much smaller range of areas here. And again, what I would do is add these two together and divide by 2, and you get even more precise, okay? But that's not what the purpose is here. It's just getting precise. But if I was doing it this way, boy, that's what I would do. So basically you see by getting smaller and smaller rectangles, you get closer and closer to the actual area. Of course you would, okay? That's all trying to show that to you. Now, let me clear my writing here so you can read what they do. Combining, I just wrote this, that was that, and then they skipped the last part. Now, can we do this any better, faster, quicker? Yeah, let's do it by using limits. Oh, no, not limits again. Yeah, they're actually going to be your pals here. They're going to help you, okay? So here's what we're going to do using limits. consider the plane region bounded by the graph of a non-negative, f is always greater than 0, not down here, so don't count this over here. Starting with A, it's positive there, it stays positive till you get to B, all in there. So there's your continuous function, non-negative continuous function, y is equal to f of x, shown here, between A and B, non-negative. The region is bounded below by the x-axis, on the left and right boundaries by the lines x equal A and x equal B, and by the top by the function values. Okay? Now, what we're going to imagine doing is taking a delta x. So what's our delta x? What we're going to do, our x is going from A to B, so the length of this is going to be B minus A. All right? Now, if you're going to do n subdivisions, subintervals, then divide that by n. B minus A divided by n is going to be my delta x. If I want just a small n here, it'll be a big delta x. Not going to do a good job of estimating, but it'll be okay for a bit. But if I want a really good job of estimating, take the n to be very large, and then this delta x is quite small. Okay? So, let's just pick a delta x here, which is b minus a divided by n. We don't even know what it is, that n is. The interval a to b is divided into n subintervals of width delta x equals b minus a over n. So that's your, now, what they show here is f operated on the right-hand end of that subdivision, but because that's a lesser value than on the left-hand end, they're going to make this little m sub I, and this is alpha of capital M sub I. And as we're going to see, as you get smaller and smaller delta x's, as your n gets bigger and bigger and bigger, then these will get closer and closer together. It doesn't matter which one's right and which one's left. It's going to come up with some value. Okay? So, don't worry about the fact that you got two different endpoints there. If you take your n's large enough and your delta x small enough, it's going to come close to a single value. Okay? So don't sweat that yet. So the endpoints of those intervals are, the first one is a plus 0 delta x, which is just a. And the next one is a plus 1 times delta x is x of 1. X of 2 is a plus 2 delta x, and so on until you get n delta x. Well, that's going to be b by delta x is b minus a over n divided by n, b minus a plus a. That's just going to be b. Okay. So your right endpoint is b, left endpoint is a, and in between is just a with some multiple, whatever your index is here, multiplied by your delta x. Because f is continuous, this function is continuous, the extreme value theorem guarantees the existence of a minimum and a maximum value of f on each subinterval. That's what your little m's and your capital M's were, your minimum and maximum, where the minimum and maximum values were. And all right. Anyone else come in since the call? Okay. We're on in Chapter 4, Integration, 4.2 Area, page 262, finding an area by a limit definition. We're sort of right in the middle of that, right close to the middle of page 462. We just are getting to this. F sub little n is the minimum value of f on the subinterval. F sub capital M sub I was the maximum value. And that's why over here, the little m was over here, because that's the minimum value there, and alpha capital M was here, because that was your maximum value there. Okay? The m sub i's are values you get here. They sort of tossed up in the notation a little bit. They're the m that gives you the maximum f, you know. So, but they capitalize the m's, which is a little bizarre. If you had been straddling this, then your maximum would have been here, your minimum would have been somewhere else. If you'd been straddling this one, your minimum would have been here, your maximum would have been one of the two endpoints there. So it really doesn't matter. Don't sweat it too much, but that's what that strange notation is representing. Okay? The minimum and maximum value of f on the subinterval. They capitalize the independent variable to give you the maximum of the dependent variable, but they don't capitalize it. A little bizarre. Okay. Next, let's define an inscribed rectangle lying inside the ith subregion and a circumscribed rectangle extending outside the ith subregion. The height of the inscribed is going to be f sub little m sub I, and the height of the circumscribed one is be little f of capital M sub I. So this is the minimum value, maximum value. For each I, the area of the inscribed rectangle is less than or equal to the area of the circumscribed rectangle. Exactly what we showed before. The area of the inscribed, our 6.48 before, was equal to the function evaluated at the minimum, at the x value that gives you the minimum value for f, times delta x. And that's less than or equal to the f value of the x value that gives you the maximum value for f times delta x, because this is bigger than that. Okay, so that's going to be that. And then the circumscribing rectangle will be equal to this part. Okay. They're trying to get a fairly simple concept really confused, okay? But don't sweat it, it'll come out. The sum of the areas of the inscribed rectangles is called the lower sum. The sum of the areas of the circumscribed rectangle is called the upper sum. So the upper sum, they're going to give the value. This time they lowercase the actual sum, which makes more sense rather than lowercasing the thing on the inside. And that's the n. It doesn't seem like that should be the argument here. Well, no, I'm sorry. This is summing all of them together. With this n, that's going to be the least sum. With this n, that's going to be the greatest sum. Okay? So this is going to be f of all your lowest m's, smallest rectangles that you would have in each subinterval times the delta x, and this would be that. The opposite. Okay. Area of the circumscribed rectangles. Okay. It will make more sense in just a moment. I sure hope. From this figure, you can see that the lower sum, that's the sum of these rectangles, are all subscribed, and the sum of the upper rectangles, the lower rectangles all underestimate the area under the curve. The upper rectangles always overestimate the area under the curve, and this is somewhere in between the two. So S of n is here for this size n, it gave you that size rectangle, less than or equal to the actual area under the curve, which is less than or equal to the circumscribed rectangle sum. Of course, it seems like you could have written that down without all the other verbiage in between. That makes perfect sense, okay? Now, then they stop, okay? And they have you do one of these. Oh boy, what a pill. Okay? Find the upper and lower sums of the region bounded by the graph of alpha of x equal x squared and the x-axis between x equals 0 and 2. Now, fortunately, okay, to begin, we partition 0 to 2 into n subintervals, each of width delta x is b minus a, which in this case is 2 minus 0, so that's 2 divided by n, whatever your n happens to be here. Okay? So that would be 2 over n. Good. They finally got to it. Okay? That's your delta x. All right? Now, because this is a monotonic function here, strictly going up, your inscribed rectangles are going to be the left-hand endpoints, and your circumscribed rectangles are going to be the right hand. So just back to what we had before, You don't have to do max and min and those kinds of things. You could just look at them and tell that. Now this is with n equal 1, 2, 3, 4, 5. Both of those, for some reason, they're really liking 5s here. But it can be anything. But your inscribed rectangle is always going to be less than the extra area. Circumscribed rectangle is always greater. Okay? Because f is increasing monotonically on the interval, the minimum rectangles occur at the left endpoint, the maximum at the right endpoint. That's what we just said. So the left endpoints are going to be, these are going to be the lower ones because this is the lesser. 0 plus I minus 1. Okay. The 0 is because that's your A. That's where that 0 comes from. I minus 1 times 2 over n because we're on the left-hand endpoint. So that's why you do I minus 1 because you want your I to start with 1, not with 0. So 1 minus 1 would be 0 times this. So that gets you to 0. So this would be 2i minus 1 over n if you multiply those up. Okay, the right-hand endpoint, again, you're starting at 0. You're doing I times 2 over n. You don't need the minus 1 because that's starting is 1, 2, 3, 4, 5. This was needed to start at 0, but because I starts at 1, you did I minus 1. This is starting at 1, and I is 1, so you just, that, so it's 2I minus 2I over n. Now, if you broke this down, you would see this is 2I over n minus 2 over n, which if they just said that, that could take care of a lot of things here, but they're not mentioning that yet. Okay? So, your lower sum is then doing this one. Okay? And just like we did before, you could pull out the 2 over n here. Okay? And then you could even pull out the 2 over n from here, because that's going to be a constant. See, these don't depend on I at all. Okay? So that's why you can pull them out of the sum. Okay? Oh, no, I'm sorry. You can't pull out because this is the function here. And this would be, the function is just that squared. So it would be a 2 over n squared. But they're not using, I'll show you. Okay. Yeah, here we go. The function is just squaring that. Okay? So this 2 over n could come on the outside. This 2 over n squared could come on the outside. So that gives you 8 over n cubed, all on the outside here because there's no other terms here. And then you're just doing the one that we did before, I minus 1 squared, which is I squared minus 2i plus 1. Okay? And let's see if they do that. Yeah, but they leave it inside the sum. I don't know why. Maybe they're going to pull it out next time. Yes, they finally pull it out here. They pull out the 8 over n cubed here, and then they have this one minus this one, just like we did last time, but they didn't show it to us last time. Okay? And then we write down what those sigma notations for your i's are. Okay? And that would be 8 over n cubed. And this one, remember, was n times n plus 1 times 2n plus 1 over 6 minus 2 times n times n plus 1 over 2. And that just came out plus n. Okay? Now, if you would do, it's tedious, but if you would do the math on that, multiply all those things together. Now, they skipped a bunch of steps. Do you need to see those done, or you see where they got them? I'll be glad to do them if you need me to. Anybody? Want to see them or not? Huh? You do want to see them, okay? So let's do the math, okay? It'll be easiest to do these two first, okay? That's 2n squared, okay? That's the first. The outers would be plus n plus 2n, that's plus 3n, and then the last would be plus 1, okay? Multiply that by n, and that just dumps up the exponent by 1 everywhere. So that 2 becomes a 3. That becomes a squared, and this becomes an n. Okay? So that's the first one, and that's over 6. And then this will be minus 2. Well, wait. Just get rid of the 2's, okay? That's legal in most states, okay? Okay? And this will be an n squared. I'm going to do the minus sign across there. That's minus n squared minus n. And then here you get a plus n. Well, the plus n and minus n go away. Okay? And that gives you, now I'm not going to skip quite as many steps as they did. They skipped off a lot, didn't they? Okay. I'm going to take this term here and do it up here. 8 over n cubed times, doing the same thing to it. When we did this, we got 2n cubed plus 3n squared plus n over 6. And then they have just a minus n squared left. Okay? But that's not over 6. So to put it over 6, it would be a minus 6 n squared over 6. Okay? Now, what that does for us is, I'll write it out, 8 over n cubed times 2n cubed. And here you have a plus 3n squared minus 6n squared. That would be a minus 3n squared plus n over 6. Okay? And 2 will go into 8 4 times, 2 will go into 6 3 times. Okay? And that's where you get 4 over 3 n cubed times 2n cubed minus 3n squared plus n. Only they put parentheses in, not braces anymore. So that's how they got to that one. Okay? So that's the summation of all those that came from your alpha of x squared times delta x. Now, all these are on the outside. Well, this is what you got. Now, at some point here, it just seems like to me we've got to do something like let n go to infinity. Okay? Because this is going to be for any n you happen to choose, this is going to give you some number. So let's just keep choosing bigger and bigger n's, but I don't want to do all that with bigger and bigger n's. Let's just rewrite this as 4 times 2n cubed over 3n cubed minus, let me go on and multiply those, 12n squared over 3n cubed plus 4n over 3n cubed. Well, guess what? Here the n squareds go away, and that first term becomes 8/3. And then these, n's, well, 3 will go into 12 4 times, and that will, 2 of the n's go away, and you're left with an n there. This time, only one of the n's goes away, you're left with an n squared there, and you got that. Well, guess what? Who cares? As n's go into infinity, This one's going to 0. This one's going to 0, because 1 over a big number is going to be something close to 0. Your answer is 8/3. Okay? And that's exactly what they wound up getting. I'm sorry, I jumped the gun on them. Let me erase mine and let you see what they did. Okay. Exactly what I just did. Multiply these two, you get 8n cubed over 3n cubed. Well, the n cubes go out, that gives you 8/3. Here we get the 3's will go out here, so you get 4n squared over n cubed, which would be 4 over n minus 4 over n. And this one will give you plus 4/3 over 4 over 3n squared. Because that n takes 2 of those out. 1 of those out, leaves you 2. Okay? This is going to be your lower sum, 8/3. Wait, I'm sorry. As n goes to infinity, these are going to go closer and closer to 8/3. When n is a big number, no, a small number, then these will be significant. In fact, they might overwhelm this. But if you get n bigger and bigger and bigger, these get smaller and smaller and smaller, so you're getting closer to 8/3 as your lower sum. If you do the upper sum, then the only difference here is your f of 2i over n. This is just going to be 2i over n squared. Remember that your function was a squaring function. So again, you can pull out the 2 over n. There they square it. You could pull out the 2 over n and the other 2 squared over n squared. Pull those out of the sum. Well, they leave them in there now, but it's going to be that. Then they're going to pull them out. There they pull them out. And then the summation of the I squared is just your n times n plus 1 of 2n plus 1 over 6. And when you multiply these together, you get the same thing we got before. 2n squared plus 3n plus 1. And then when you multiply it there, that would be 2n cubed plus 3n squared plus n. And if you let those cancel out, let me, it'd be 8 over n cubed times what we just said, 2n squared, no, 2n cubed plus 3n squared plus n over 6. If you multiply those together, this will be a 3 here and a 4 here. And you wind up with multiplying all those together. 8n cubed over n cubed, so that would be 8/3 plus, and this would be 4 over n, because it would be n squared over n cubed. Okay, and the next one will be plus 4/3, 4 over 3n squared. Okay, but and this would be the upper sum. You let n get larger and larger and larger. That goes to 0. This goes to 0, and you wind up with 8/3 again. Guess what? Upper and lower, as the n gets closer and closer to 0, they get closer and closer to the same third thing, which is 8/3. This is exactly what we had here, 4n cubed over that thing. Okay, 4/3 n cubed over that thing. When you put n cubed under each one of those, it gives you 8/3 plus 4 over n plus 4/3 over n squared. Okay, or 4 over 3n squared. And again, let n get bigger and bigger and bigger. That's getting closer and closer to 8/3. Either from the big ones or the small ones, it doesn't matter. You got the same limit. Okay. Now, this next theorem shows that the equivalencies of the limits as n's go to infinity of the upper and the lower sums is not mere coincidence. It's true for all functions that are continuous and non-negative on the closed interval A to B. Which, of course, if the interval goes smaller and smaller and smaller, the pluses and minuses, the largest and the smallest get closer and closer together. Okay? So it's nothing new. All that was just to get to this. Okay? The limits of the lower and upper sums let f be continuous and non-negative on the interval from A to B. That's the requirement. It has to be a continuous function, and it always has to be greater than 0. The limits as n approaches infinity of both the lower sums and the upper sums exist and are equal to each other. Therefore, the limit as n goes to infinity of the lower sum is equal to this, and that's the same as this, and that's the same as the limit of the upper sum. As the n gets closer and closer to infinity, those upper and lowers get closer and closer to each other until they're the same. Okay, where delta x is b minus a over n, and of course as n is going to infinity, this is getting incrementally small. F sub m, little m, F sub capital M are the minimum and maximum values of f on the ith subinterval. But it doesn't really matter. As n's going to infinity, those subintervals are getting closer and closer together, meaning the difference between the max and min is getting down to the same value. Okay. In theorem 4.3, we just had the same limit is obtained from both the minimum F sub mi, little mi, and the maximum value F sub capital Mi. So it follows from the squeeze theorem, theorem 1.8, this is it, that the choice of x on the ith interval does not affect the limit. Okay? In other words, which x do you use on that interval? It doesn't matter. Choose any old x in that interval. Okay? And you're going to get it. So if h of x is less than or equal to f of x less than or equal to g of x, where h of x is the lower, g of x is the upper, f of x is something in between. If those are all true, if that's always true for all x in the open interval x containing c, except possibly at c itself, then the limit, if this is the same as the limit there, the limit f has to be the same. Okay? Squeeze theorem. Going back to that. Okay. So what does all that mean? It means you're free to choose any arbitrary x value on the I subinterval shown in the definition of the area of the region in the plane. It doesn't matter which one you choose. Any one you choose. Because guess what? You're letting your delta x go closer and closer to 0. So as long as there's something in there, soon you're going to be at the only value left. That f be continuous and non-negative on the interval a to b, same as before. The area, this is the definition of area of a region on a plane. Area of a region bounded by the graph of f, the x-axis and the vertical lines x equal a and x equal b, is the limit as n goes to infinity of the summation of this thing, delta x. Doesn't matter where you choose your c to be. Right hand, left hand, min, max, it doesn't matter, just anything on the interval of delta x, where delta of x sub I is always less than or equal to c sub I is always less than or equal to x sub I. This is going to be that. It doesn't matter the value, as long as this is getting closer and closer to 0, you're getting closer and closer to the area under the curve. Okay? That's what it gets down to. So, find the area of the region bounded, oh boy, here we go again, by the graph of f of x equal x cubed, the x-axis and the vertical lines x equals 0 and x equal 1. Okay? Remember, x cubed comes up from here and does this. We're not going over here because that goes negative. So we can't start anywhere beyond 0, 0 here. We could go anywhere on that side, but nothing on this side because that starts going downhill there. Okay? So here's going to be the function, the cubic function, and the area of the region bounded by the graph. There it is. Okay. Now they've just shown a rectangle there. Why they chose that one, it doesn't matter. Okay? Any old rectangle. I would have chosen one right in the middle. You know, it had some of it less and some of it greater. Doesn't matter where you choose it. Okay? All right. Here is Miriam. Huh? I'm sorry. Joy, you got it. I'm sorry, I knew that. Okay. All right. Good deal. Watch out. I may sometimes get carried away with some of this. Ooh, pretty close. What we normally do is break time. Let's see if we can get through this example first. Oh, wait a minute. I just noticed we've skipped example 4, haven't we? Yeah. No, that we did example 4. I just hadn't turned the page. Yeah. Sorry about that. All right. So, yeah, we are on example 5. I just hadn't flipped the pages. Okay. All right. Do you want to start example 5 before break or after break? Or do you want a break? No break? No break? Let's take one now or wait till we do example 5? Second? After example 5, okay. Find the area of the region bounded by the graph f of it, blah, blah. We've already talked about that, okay? Now, how in the world they gave you this answer right now? I do not know. That is just absolutely crazy that they do that before they even show you how to do it. But forget that. They're just saying it is that, but let's see what we can. Begin by noting that f is continuous. It is non-negative on the subinterval from 0 to 1. So let's partition 0 to 1 into n subintervals, each with a width of delta x equal b minus a, 1 minus 0, divided by n. So there's your delta x. Okay? Now, according to the definition of area, you can choose any x value in the ith subinterval. Any one. Okay? For this example, they chose the right endpoint. I don't care. Just as good as any. C sub I is I over n then, every time. Okay? Because each subinterval is going to be that. So the value for the right endpoint will be I over n. That's very nice and convenient. Okay? So, the area under that curve would be the limit as n approaches infinity of the summation of x equal 1 to n of f sub c sub I times delta x. Okay. Now, we know a lot of those things, so let's just write them down. Well, first, the limit as n goes to infinity of the summation of I equal 1 to n. Now, what's your f sub c? C cubed, isn't it? Right? That's what our function was. Function was f of x is equal to x cubed. So it's going to be c sub I cubed. Oops. C sub I cubed. But here's your c sub I. So that's going to be I cubed over n cubed. Okay? Times the delta x, which is 1 over n. Okay? All right with that? All right. Now, this one's actually going to work out pretty nicely, I think. It's going to be the limit as n approaches infinity. Now, pull everything except the things with i's in it outside the thing. So that would be 1 over n fourth. Because those are not bothered by the summation. And then we just have the summation I equal 1 to n of I cubed. Okay? Now, I want to flip back on the slides, but it's just so many flipping. If we go back a few pages in the book, you'll see I cubed is n squared times n plus 1 squared over 4. Okay? So this is going to be the limit as n approaches infinity of 1 over n to the fourth And then that I just said was n squared times n plus 1 squared over 4. Let me go back and check and make sure I said it right. N plus 1. Yeah, that's it. Okay? Now, all we have to do is multiply. So let's first expand this. That'll be n squared plus 2n plus 1 times n squared. We'll make it n to the 4th plus 2n cubed plus n squared. Okay? So that will now be the limit as n approaches infinity of 1 over n to the 4th times n to the 4th plus 2n cubed plus n squared over 4. Okay? Now, let me erase this little line here that's getting in the way a moment here and do what we can do. The limit, you can pull the 1/4 out front, so that's 1/4 times the limit as n approaches infinity of n to the 4th over n to the 4th would be 1 plus 2 over n, that's 2n cubed over n to the 4th, that's 2 over n, plus n squared over n to the 4th would be 1 over n squared. That's an ugly 1, isn't it? Okay. Okay, let me go on. Oops. All right. My computer's lost its mind. Oh, there it is. I've lost my mind. I don't know which. Let's get rid of this part so it's not as confusing. Okay. Now, I can take the limit as n's going to infinity here because 1 over infinity goes to 0, or 2 over infinity goes to 0. 1 over infinity squared goes to 0. So this is just 1/4 times the limit of 1 is 1. So that's 1/4. And that's how they could go back and say that that area under the curve is 1/4.
So why you stretching them too out?
Because 1 over, as n's going to infinity, 2 over 4 million. That's a pretty small number, right? And 2 over 4 million squared is even a smaller. 1 over 4 million squared is even a smaller number. They're going to 0. Anything over something going to infinity, if something is infinity in the denominator, it's going to 0. Because you've got something over a very small number. Just think of 1/2, compare that to 1/10, compare that to 100, compare that to 1,000. You know, they just get smaller and smaller and smaller. Okay? And 1,000 is nowhere close to infinity. Just keep getting smaller, and you're disappearing. It's just 1. The limit of that is 1. 1/4 times 1 is 1/4. Okay. Now let's see how they do it. They perhaps do it a little bit neater. Oh, how could that be? Let's see. Oh, wait. Oh, okay. So I think they do the same thing we just did. This becomes 1 over n cubed times 1 over n. So that's 1. I mean, this is I over n cubed times 1 over n. All the n's can come out. They keep it inside. Yeah, they put it outside the summation finally. Okay, you can't come outside the limit because that involves n, but the summation doesn't. So you just have an I cubed left there. But what is that summation of I cubed? Exactly what we found. N squared times n plus 1 squared over 4. We went back and looked in book 2. And this is what you have. When you multiply those out, they get, well, they show how to multiply them out. But you square that, and that's n squared plus 2n plus 1, and multiply by n squared, that would be n to the 4th plus 2n squared plus, 2n cubed plus n squared over 4. And then combine these with those, and 1/4 as well. so much easier to take the 1/4 on the outside and not have to mess with the fractions. But if you do, you wind up, as that n goes to infinity, that goes to 0, that goes to 0. So you wind up with 1/4. Okay. The region, the area of that region is 1/4. So that's what they said in their first illustration before they ever showed you how they got it. In general, a good value to choose is the midpoint of the interval and apply the midpoint rule. That's easy enough to say, but if it makes the calculations really nasty, why do that? But, you know, that would give it to you sooner, but guess what? If you're going to the limit as n goes to infinity, it doesn't matter what point you choose. The midpoint rule will get you there sooner if you're just doing it one step at a time. But that's where we left off. Now, example 6 is the next one. Is this the place where you want to take the break? Okay. We just got example 6, 7, and 8 to go. So when we come back, we'll start example 6 here. So let's take a quick break and do example 6. Now, by the way, this is especially probably important for those who may not have books, but even if you do, example 6, you can go to larsoncalculus.com. Absolutely free website. You don't have to own the book, buy the book, or anything else. Free website. Anyone can go there and see an interactive version of this type of example. Okay? It says, find the area of the integral of the region bounded by the graph of f of x is equal to 4 minus x squared. The x-axis, the vertical lines x equal 1 and x equal 2. Okay? Now, if you got a book, you can see a picture of that. I'll try to draw a rough idea of what that is. If this is 4, 2, 1, 3, 1, 2. Okay? It's a parabola doing something like that, and you're doing the interval, the area here between 1 and 2. Now 2 is right where it goes to 0, so you couldn't go any past 2 or else you'd be in the negative territory, but that's the interval that we're talking about. So if we choose a little dx here, delta x here, and that represents some little rectangle here, any value on that you could choose. Now, things to note. This is a continuous function. It's a polynomial function. All polynomials are continuous everywhere, especially between these two limits, 1 and 2. Okay? It's not negative, just barely. It goes negative just past 2, but at 2 it's not negative. Okay? And so begin by partitioning into n subintervals, each of with the delta x is b minus a, which is 2 minus 1 over n, which is just 1 over n. Right? All right. Now, your c sub I, that's what you're going to need next, c sub I is just going to be, all right, you're starting here at 1, okay, so it's going to be 1 plus I times your subinterval over n, 1 plus I over n, because you're starting at this end, which is 1, and then each subinterval, you're going to do 1 plus delta x. Well, delta x is 1 over n, right? So the first one will be 1 plus 1 over n, the next will be 1 plus 2 over n, 1 plus 3 over n. So this one's going to be 1 plus I over n, because you're your ith interval out here of that delta x. So 1 plus I over n. The 1 is because this is where where it starts, and I over n means you went I subinterval to get there. Okay. So, what your the area is going to be is go straight to the limit definition. The limit as n goes to infinity of the summation of your f sub c of I, which would be this, and I'll write it out, f sub c of I times delta x. That's the height times the width, okay? And this will be as I goes from 1 to infinity, okay? I'm sorry, 1 to n. N's going to infinity, so I was sort of skipping a step there, but I should, since I've got it written there, put it in 1 to n, okay? So, it's f of c sub I don't know why I wrote it as a subscript, okay? Now, here's your f. So this will be the limit as n goes to infinity of the summation of I equal 1 to n. Now your f of c sub I would be 4 minus c sub I, whoops, put my parentheses in the wrong place. C sub I squared, okay, times your delta x, which is 1 over n. I'm going to pull that 1 over n out here. There's no reason to have an n there. Well, there is for future reference, but for right now, doing these is not important there. But what is that c sub I? So this will be the limit as n approaches infinity of 1 over n times the summation of I equal 1 to n, where your c sub I is 1 plus I over n. And that is what you plug in here. So this will be 4 minus, let me rewrite that as n plus I over n. Is that okay? This 1 plus I over n, let me write this as n over n for 1. That'd be 1 plus I over n. That's going to make the calculations maybe a little bit easier. Okay? So c sub I, 4 minus c sub I squared, and this is your c sub I, so it's going to be n plus 1 n plus I squared over n squared. Okay. Now, I'm rapidly running out of room. Story of my life. The limit as n approaches infinity of 1 over n, later going to take more out, but we're going to start with that. The summation I equal 1 to n I think this is as good a time as any to make that 4n squared minus n plus I squared over n squared. See what I did there? You had a 4 out here by itself, and this thing is over n squared. So let's just do 4n squared here minus this thing squared. That is plus, yeah, I believe it is. Yeah, and that's over n squared. Okay. So now I'm going to take the other n squared out. So this becomes the limit as n approaches infinity of 1 over n cubed times the summation I equal 1 to n. Now, the 4n squared is just 4n squared. Okay, well, it's going to be more than that. When you square this binomial, this is an n squared plus 2ni plus I squared, right? So you got 4n squared minus n squared, so that's, I guess I should do it. Okay, I'm going to have to erase, I think, my drawing here because it's getting in the way. Okay. Yeah. Okay, wait just a second. Okay, when what? Right here? Or what? Or before
Where
that?
did you get the n squared? 4n squared.
Okay. Here was my sum right here. 4 minus this over that. So to get it over a common denominator, I make it 4n squared over n squared. Right? So that's where that came from. So I put it over the same denominator. And now what I'm going to do, that's 4n squared. Now I pulled out the denominator part, minus, and here's this, so it would be minus n squared minus 2ni plus I squared. Yeah. And all that, well, no, I've already pulled the n squared out. Okay. Well, obviously, you can lose one of these and make it 3n squared plus, okay. So there's my summation. All right. I'm going up to the top with this and make this the limit as n approaches infinity, 1 over n cubed times the summation I equal 1 to n of 4n, no, that's a 3n squared now. I just subtracted 1 from it. Three n squared minus 2ni plus I squared. All right. Now, the limit as n approaches infinity, I hate writing all these things over and over and over, over 1 over n cubed, but if I don't, I'll forget about them. Okay, now that first summation there is 3n squared summed n times. So that's going to be 3n cubed, right? It's 3n squared plus 3n squared plus 3n squared plus 3n squared n times, so it's n times 3n squared, so it's 3n cubed. So that first one is going to be 3n cubed, okay? Minus 2n times the summation I equal 1 to n, sorry, of I plus the summation I equal 1 to n of I squared. Okay. Now, again, I'm running out of room really badly. So I think I'll erase my first line down here. I really don't need this line either, so I'll erase that line. Okay? Because we've already used that. I'll just use my problem, leave my problem there, and that's all. Okay. Whoops. Hit the wrong key. There we go. So what this is equal to is the limit. This is coming from here to there. Okay. As n goes to infinity, 1 over n cubed times the summation of Oh, wait. Too far over. Let's do my brace and then do the 3n squared, 3n cubed, because that's there, minus 2n times the, oh, we don't need that sum anymore because we know what that is, right? I, remember what that one was? Let's see, let's put this in a bracket here. That was n times n plus 1 over 2, wasn't it? Go back a couple pages, 3 or 4 pages now, to that one. Summation of I equal 1 to n of I is n times n plus 1 over 2. Okay? Plus, and that next one is n times n plus 1 times 2n plus 1 over 6. That's our I squared that we've used several times now. N times n plus 1 times 2n plus 1 over 6. Okay. Now, I probably should leave the area there because that's what we've been doing. So, haven't been dragging that along, but let's drag it along now. It's equal to the limit as n approaches infinity of 1 over n cubed times 3n cubed minus. Okay. Now we got to multiply these together. Well, first the 2's will cancel out, so that'll make it a little nicer. And that will be just n squared times n is n cubed minus n squared. Minus n cubed minus n squared. Okay. Where did that come from? N times n times n, that's the minus n cubed, and n times 1, that's the minus n squared. Okay. Now the next one, not as much will cancel out, but let's see what we've got. That will be plus, but that n is still in front there. Wait a minute. I didn't close out here. I should have, sorry. And this should be a brace here. Okay. Sorry about that. I used the wrong grouping symbols. Okay. Oh boy. We've done this before. This is 2n squared plus 3n plus 1. Okay? And then multiply that by n, and you get 2n cubed plus 3n squared plus n over 6. Okay? I need more room, so let me erase another line here. This is so tedious, and once you learn how we get to the end of it, it's just like doing limits with derivatives. It's such a pain in the neck until you learn the derivative rules, and then you don't have to do it anymore. This is the limit as n goes to infinity of 1 over n cubed times, now let's combine like terms here. 3n cubed minus n cubed is going to be 2n cubed, but we're going to need to put that over 6, so that would be 6n cubed. Okay? And then we've got a minus n, minus n squared. We're going to need a 6 over that, so it would be minus 6n squared plus 2n cubed plus 3n squared plus n. Okay? All this now is over our 6. So all I did was I combined these two like terms and then brought the 6 times, ooh, I didn't do it right though, did I? This is 2n cubed. I brought the 6 up, this should be a 12n cubed. Sorry about that. n cubed. Okay, because I put it, again, brought the 6 over here, but I subtracted first, so the 2 of them, 2 times 6 is 12n cubed, minus 6n squared, okay, and this is a minus of all this, okay, and then plus 2n cubed, because these were already over 6. Now we can combine like terms there, so let me erase another line down here. I'm sorry these are so tedious, but they are what they are. After a while, we won't need to ever, well, I won't say ever, but do this much anymore. Okay, that's the limit as n approaches infinity of 1 over n cubed. Now, let's combine all these things together. That will be 14, goodness, that looks weird, n cubed minus 3n squared plus n over 6. Okay, I'll try to fit that in here. The limit as n goes to infinity. If we combine the n cubed in there and do all the other things, so let's, that first one would be 12 over 3, no, I can't do it, 7 over 3. That doesn't seem right, but we'll come back and get that. 7 over 3, and that'd be n cubed over n cubed, so those go away. Minus, okay, the first one came from 14 over 6, 7 over 3, n cubed over n cubed, you lose the n cubed. Then you have a minus 3 over 6 would be 1 over 2, so 1 over 2n, that's the second one, okay? And then the third one is plus 1 over n squared. Now you take the limit of that as n goes to infinity, these go to 0, this goes to 0, and you're left with 7/3. Now that seems like a totally weird answer. It's supposed to be 5/3. I messed something up somewhere. Yeah.
On that section.
Here? Here? Yes.
You did multiply n times n squared. Then don't you have to multiply that n on the outside times the n squared plus n?
Yeah. Yeah, when you multiply these together, you get n squared plus n.
Yeah.
And
then you
then
gotta multiply that n again.
yeah, and that gives you
N cubed
n cubed.
plus n cubed.
Yeah, okay. Right. Yeah, you're right. Okay, but there's a minus sign in front of it. So, okay, this is from here. This comes down here. Okay, and then, just like you said, this is going to be minus, and n times n times n is minus n cubed. So that's where that one comes from.
So that'll leave you with 2.
What's that?
That'll leave you with 2.
2n cubed.
So
And-
that's for 3n cubed for 2.
Well, I've still got them both here.
Oh.
Yeah, the next time it's going to go to 2n cubed. Yeah. But somewhere here I screwed up somewhere. Let's see if I can find it quickly in the book.
I think you were supposed to do.
What's that?
I think you're supposed to have like a part at the very top. You've got plus the thing with the I squared. I think it's supposed to be minus.
Up here?
Over one more.
Over
No.
this
The
one?
last summation.
This one.
Yeah, I think
It
that's
should've
supposed to be
been minus.
minus, not plus.
Okay. Is this right? It may not be. That's what I'm asking you. I've already erased where it
I
came
think
from.
it's supposed to be minus.
You
I
think that was
squared.
supposed to be a minus there?
Yeah,
If so, that
last
would
one.
account for it.
Yeah.
Okay. I just can't see where it came from, so I can't remember where that drew
Because
from.
that, well, yeah, we erased that part.
Yeah, I've already erased it. It came from here, I bet. That
Yeah.
minus sign should have carried through, and it probably didn't. So yeah, you're probably right. So that would have been one extra there, subtract them off, and it probably gave you a 5. So 5/3 is your answer. Okay. Sorry about that. It should have been a 5/3. Okay. So, but you can go to the larsoncalculus.com and see that done correctly. And it's all there, interactive, and you can do it. Let's try to do number 7 and hope that it's not quite as, it's probably going to be worse. Let's see if we can get by with fewer errors. Find the area of the region bounded by the graph of f of y. Uh-oh, we haven't done many of those. F of y is equal to y squared. But this might actually turn out being easy because it's a pretty simple thing. And the y-axis for 0 less than or equal to y is less than or equal to 1, as shown in the figure. Now here is how that one looks. It's half of a sleeping parabola, going from 0 on x to 1 on x, and going from 0 to 1 on y too. But here we're doing delta y's. And you can close up these rectangles however you want to, but this is what you're doing now. Okay? You're doing delta y's now. Okay? And the y is going from 0 to 1. Okay? Now this f is continuous because it's a polynomial function. It's always positive. Doesn't ever go negative. The y is never negative. The x is never negative. Nothing's ever negative. It's 0 to 1 there. Everything's within the things there. And you can still use this basic procedure you did before. Begin by partitioning the interval into 0 to 1 into n subintervals. So your delta x is equal to 1 minus 0. Oops, it's a delta y though. Delta y is equal to 1 minus 0 over n, which is 1 over n, just like before. Okay? And your function, pick a c, any c, but this c is going to be of y now. Okay? So just pick this c here, c sub I here. And your f of c sub I is going to be c sub I squared. But what is your c sub I? It's 0 plus I. The c sub I is equal to 0 plus I over n. Because you go up I intervals, 1, 2, 3, 4, 5 intervals, or whatever it is. So there's your c sub I. Okay? So your f of c sub I is equal to I over n squared. Okay? This is easier because you don't have that leading 1 there or anything else like that. Okay. Now we can do our sum, or the limit actually. The area is equal to the limit as n approaches infinity of, I'm going to pull out the 1 over n here. That's your delta x. That's going to be the same for all of them. The summation from I equal 1 to n of I squared over n squared. Well, that n squared isn't going to hurt anything, so pull it out. and make it with this. That's the limit of n going to infinity of 1 over n cubed of the summation of I equal 1 to n of I squared. And we know that one. It doesn't change whether it's x's or y's. This is the limit as n goes to infinity of 1 over n cubed. And what's that summation? I squared. Pretty sure that was n times n plus 1 times 2n plus 1. We've done it enough today over 6, right? Nothing else to multiply or do anything else with, so let's just do that. And this is the same binomial we've done before, 2n squared plus 3n plus 1. Multiply it by n and you get that's cubed. So what we have now is the limit as n goes to infinity. That's a pretty ugly infinity, but you get the idea. 1 over n cubed of, and your numerator here is 2n cubed plus 3n squared plus 1 all over 6. Okay? I feel like I'm doing this too fast and skipping something, missing something here, but let's just see what happens. What's that? What'd you say?
I said we just skip this whole section.
No, from here, I mean, you've done the hard part, okay? Let's just clean this up a little bit and make this the limit as n approaches infinity. That first one is 2n cubed over n cubed, 2/6 n cubed. Well, 2/6 is 1/3. N cubed over n cubed is 1, okay? The next part is 3 over 6, which is 1 over 2 n, because you had an n squared in the numerator, n cubed in the denominator. And the last part is 1 over 6 n cubed. Okay? No, I'm sorry. This is an n here. N squared. Okay. It really doesn't matter what it is, because guess what? That goes to 0. That goes to 0. Okay? So our answer is 1/3. Okay? And I think you see in the book, that's what they get as well. Okay. I agree with you. This is a pain in the neck to do. And as soon as we get to the next section, you'll find we can, well, it's going to take us a little while into the next section, but you'll see it does get better. Okay? Now, remember the last thing they did before this? That answer, by the way, was 1/3. When they said this thing about the midpoint rule, that should have been now, and then example 8 follows that one. Okay? And that is one with signs. It's basically doing the same thing we did. If you remember back not too long ago, we did the first lobe of the sine function. We did it with the left, we did it with the right, we did it with the things. Now it's just doing it with the midpoint rule, and it's basically the same procedure we did then, but if we went back and compared to the other, it's actually a better approximation. But I'd say, I think I'm with Tarika on this one. Let's just skip that one, because it really doesn't add anything new except a different way to do it. And it's just really tedious, okay? So let's just hang that one up for now. Now let's move on. Homework exercise is 4.2, okay? please try some of these. You got to get used to that sigma notation, the I's and all that kind of stuff. So practice some of these. Any of the odds 5 through 9, they're all at Calc Chat. 5's at Calc View. Any of the odds 11 through 15, they're all at Calc Chat. Any of the odds 17 to 23, they're all at Calc Chat. 21's at Calc View. 25 or 27, they're both at Calc Chat. 25's at Calc View. Any of the odds, 29 to 33, they're all at Calc Chat. 33's at Calc View. Try for 35, it's at Calc Chat. 37 or 39, they're both at Calc Chat. 39's at Calc View. 41 or 43, they're both at Calc Chat. 43's at Calc View. And then do 45, it's at Calc Chat. Any of the odds 47 to 55, they're all at Calc Chat. 49's at Calc View. Any of the odds 57 to 61, they're all at Calc Chat. 57's at Calc View. 63 or 65, they're both at Calc Chat. 65's at Calc View. And that is using the midpoint rule, so if you do that, I'll feel bad that I didn't do that last example for you. But if you need it, I'll come back and do that. 67 or 69, they're both at Calc Chat. 71 is at Calc Chat. There's a true-false 73's, it should be at Calc Chat. There's a writing one if you're interested in that, that's at Calc, should be at Calc Chat. A seating capacity issue, that's one usually done in another course in some sense, but 77 should be at Calc Chat. And then the Putnam Challenge only if you wanted to. But that is the end of the section. Whew. Let's get rid of that one. I'm all in favor of that. And let's go to 4.3. I don't know where the 12 came from. All right, 4.3 is introducing something that gets us just a tad closer to real integration and get you away from the summations that we've been doing. But we got just a little bit more to do before we get there. So we'll start at current slide. Any questions before we leave 4.2 and get to 4.3? All right. 4.3, Riemann sums and definite integrals. Okay, right there is another potential paper topic. Who in the world was Riemann? His name was Georg Friedrich Bernhard Riemann. Okay, German mathematician, did his most famous work in the areas of non-Euclidean geometry, differential equations, number theory, and it's also Riemann's results in physics and mathematics formed the structure on which Einstein based his general theory of relativity. So even though he lived probably, I'm guessing, at least 40 years prior to Einstein, I don't remember when Einstein was born, but I think Riemann was already dead before then, but he still influenced Einstein pretty greatly. So that's pretty big praise, that Einstein used his work. So let's move on. 4.3, Riemann sums and definite integrals. Well, first we've got to understand what in the world a Riemann sum is. So that's the first objective here. Then we'll evaluate a definite integral using limit, oh boy, and geometric formula. That sounds a little better. And finally, we'll evaluate a limit using properties of definite integrals. That's where we want to be, folks. That's where all this has been leading toward. It seems like a long, circuitous route to get here, but we're almost there. So let's start with Riemann sums. Okay? Now, if this seems similar to what we just did, it is similar, but there's a subtle little difference here. Consider a region bounded by the graph of f of x equal square root of x. The x-axis for x equals 0 to 1. Well, there you got a positive function between 0 and 1, and you know what the function is. Okay? It says evaluate the limit as n goes to infinity of the summation of I equal 1 to infinity of f of c sub I sub delta x sub I. It's exactly what we were doing in the last section, right? Where C, now they say C is the right endpoint of the partition, given by this. Now, here's the big difference. And it's not going to be obvious now why in the world are they doing it this way. But now we're going to let the C sub I. Before we had even partition. The partition was b minus a, 1 minus 0 divided by n. Now we're going to have your C sub I is I squared over n squared. Why in the world would we do that? Okay? Well, because this is a square root problem. Okay? And it's going to make life a little easier. Looks like it's going to make it incredibly difficult, but it's actually going to make it a little easier. Okay? So that's your C sub I. Your delta of x sub I is the width of the ith interval, and the ith interval is going to be variable. Down here, they're going to be incredibly small. Up here, pretty large. Okay? But up here, they're changing less. Down here, they're changing really fast. So that's part of the reason they're doing this. The subintervals do not have equal widths. Okay? So, oh, okay. Sorry, I guess I didn't realize this was the first example. Okay. Now, with that in mind, your delta I is going to be. This looks awfully messy. Okay. You're going from this point, the width here. It's not all the same, so you have to do each interval differently. Well, let's do this one since they have this one right. It's I minus 1 over 2 n minus 1 over 2 over n squared, and the previous one was going to be, no, I'm sorry. If you do this and do it for I plus 1 and I, or do they do I minus 1? Let's see. Yeah, I minus 1 to I. So if you do it that way, and this one would be I squared minus n squared. The one prior to that would be I minus 1 squared minus n, over n squared. That's where they get this one. I squared over n squared minus I minus 1 squared over n squared. Now, you think, why in the world would you ever do something like that? But let's see what happens. Let me get my pen set up. Okay, it's not set up. There we go. Okay, so this would be I squared minus, and when you square this, you'll get I squared minus a minus, which is going to be plus 2I minus 1, because minus a plus is that, over n squared, which is going to be, the I squareds go out here, 2I minus 1 over n squared. Okay? And that's what they get right here. 2I minus 1 over n squared.
You said that wouldn't be a plus
Say that one more time.
That wouldn't be a plus 1. The I minus 1 squared.
Yeah. Okay. When you square this, I'll skip some steps there. This is I squared minus 2I plus 1, right? But you got a minus sign in front of that. And that changed that to a minus, that changed that to a plus, and that changed that to a minus. Got it? Yeah. Good question. Okay. So this is going to be it for any interval. This is going to be your delta x of I. Notice that it's not nearly as simple as we were doing it before. That makes it a real pain, more of a pain in the neck. Okay? Now, so the next thing you do, since you got the width of the ith interval is this, then you do the remember what we're doing, the limit as n goes to infinity of, if I want to do the sum, I equal 1 to n of f of c sub I times delta x sub I. Huh. I don't know where my computer is going, but it's going crazy. Delta x sub I. Okay, the period came out, but that, I mean, the dot on the I was all that showed up. Okay. Now, a little bit of reminder. Your f of x here is square root of x. Okay? And your delta x sub I was what we just had here. Okay? So, what we have here is the limit as n goes to infinity of the summation of I equal 1 to infinity, 1 to n. Usually you just write one thing and not the limit. I can't get my eraser to come up now. This is acting so incredibly crazy. Okay. Let me try my eraser one more time. There it is. That's an n there. Okay. Now, your f sub c, remember, was the square root of c sub I. Okay? And your x sub I, the delta x sub I, I wrote it there, but they wrote it here, times 2I minus 1 over n squared. Okay? That was your delta x sub I. Okay. Go back and just remind you. But here's your c sub I squared over n squared. Okay? And that's where the magic comes in here. This will now be the limit as n approaches infinity of the summation I equal 1 to n, but the c sub I was, remember, I squared over n squared. So this will be, square root of that would be I n. Okay? I squared over n squared, square root of that would be I over I times n times 2I minus 1, sorry. Over n squared. Okay, well that n will wipe out one of those anyway, and what we have now is the limit as n approaches infinity of the sum, that's an ugly sum, isn't it, I equal 1 to n of 1 over n, I'm going to pull that on the outside, that's what's left over there. What you have is 2I squared minus I, okay, which will then be the limit as n goes to infinity of 1 over n okay, times 2 times the summation I equal 1 to n of I squared minus the summation I equal 1 to n of I. Okay. Now, but those are both things that we can do. We have done multiple times now. Okay? This certainly started off looking messier, but by the choice of your partition to be something that's undone by your function, actually turns out to be something that looks like probably a good idea. Is it replicatable? I don't know. Let's see. That'd be the limit as n approaches infinity of 1 over n times 2. Now, we know what that is. We've done it often enough now. That's n times n plus 1 times 2n plus 1, I can't write, over 6 minus n times n plus 1 over 2. Okay? Now, this is beginning to look like we're in serious trouble here, and I think we are. One place we're in serious trouble, if you remember where I started, I had a 1 over n squared, and suddenly I made it a 1 over n. And I'm so sorry, huh? I think I've erased the line I did. Yeah, sorry. And it, boy, did I ever blow it. Yeah, you'll need to follow the one in the book. I'm sorry. And I'm using too much time to get there. That's supposed to n cubed here, and I lost an n squared miserably. I'm sorry, that's n cubed. Okay. Because got to have an n cubed because you have n cubes in the numerator too. But you wind up, and you'll have to go back and follow from the book, because I just completely dropped. I think it was that n squared right there that I dropped, and then did 1 over n squared that I messed up too. Sorry about that. But as soon as I saw 2 more n's in the numerator than we had in the denominator, I knew we were hopelessly lost here. But it does come out, and if you follow the math on through, you wind up with if you just use the leading terms here, remember this one has a 2n cubed. The rest of them don't really matter. It starts with a 2n cubed, and you have a times 2, so 6 will go into one of those 3 will go into that, and 2 will go into that 1 time, 2 will go into 6 3 times. So your only term that comes out of it is 2/3. And I'm sorry, I messed up the 1 over n's pretty badly there. But the area there is, now I think the book either messed something up too, because they show a 2/3 on the calculation and a 1/3 by the picture. And it really should be 1/3. And I don't know where they made their mistake. But they did. Oh, I'm sorry. No. Sorry. They are doing something rather bizarre here. No. The area under that curve is 2/3. That's correct. But what they're doing in the book, and I know the reason they're doing it, but it seems so strange to do that. The area under here is 2/3. The area inside the box is 1, so the area up here is 1/3. Well, that's not what the problem was asking about, but that's the same 1/3 we got when we did the parabola that went like this, and we got a 1/3 that way, and they're just showing you that came up the same thing. Now, why they chose that particular instance to throw something like that into it, I'm not sure, okay? But let me go on and erase my scratch here and see if we can salvage anything here from the problem. Your delta x of I was, as we did, we carried it on through, it had 2I minus 1 over n squared. I think I dropped the n squared, okay? I've made it just an n, okay? So the limit then is the limit as n goes to infinity of summation I equal 1 to n, L sub c, okay? And when I flip back to do the L sub c, c was 1 squared over n squared, and I think I wrote 1 squared times n squared when I did my math. I erased it so I can't see it now. So anyway, it's the square root of I over n, okay? So the delta x of I was this, 2I minus 1 over n squared, and this was the square root of I squared over n squared, which is I over n. These two say again. I did I-N, and then it wiped out one of those, and that's where I made my error, okay? This is I squared over n squared, and square root of that would be I over n. So that's the point where I really screwed it up, okay? So then you have, and now they skip a bunch of steps here. This becomes I over n. So I times 2I would be 2I squared minus I. That part we did right. And this would be square root of n squared of n times n, so you have 1 over n cubed. Okay? And this comes up being 2I squared over minus 1, which is just like what we did. 2I squared minus I. It just should have been 1 over n cubed out front. Okay? And this would then be 2 times, just like we did, n times n plus 1 times 2n plus 1 over 6, and then the final I out here is n times n plus 1 over 2. That's a subtraction there. And when you do the math there, and it would be so simple to 2 into 6 would be 3, go on and change that to a third. They don't do that, and I don't know why they don't do that, but I wish they had. You should wind up getting the same answer. In fact, you do. If they had just taken that out and made that a 3. This, remember from many times we've done it before, this would be 2n cubed plus 3n squared plus n minus n squared minus n, just like I think we did before. And that gives you except these are over 2 and those are over 3. And that's maybe doing their way will make it better. The deal is, these with the n squareds and n's, they really don't matter. The only thing that matters is, but of course you have to get least common denominator, so that does matter. And that should have been 6, so that's probably why they continue with the 6. Yeah, that is why they continue with the 6. So don't do this, okay? But then this one, and it's like I did it. Multiply this by 3 to give you a 6, and multiply these by 3 also. Because now that gives you exactly what they've got now. 2n to the cubed, and then the rest of them don't really matter, because when you divide by n cubed, these parts are going to go away, and you're left with 2/3. Okay. But I'll let them do it. Sorry. I'll erase my part. They skip a bunch of steps here, but the point is you get 4 over 6, 4n cubed over 6n cubed is 2/3. 3n squared over this would be 1 over 2n. This is 1 over 6n, minus 1 over 6n. As n goes to infinity, that goes to 0, that goes to 0. So you're left with a limit of 2/3. That's the only one that counts. Okay. Now, we know the region shown here as an area of 1/3 because they went back and did the one that was upright like this, and that region under there was 1/3, and this is a square of 1, so it allows that to be 2/3. So the area bounded by that graph, which this wasn't the original problem, and this is what sort of drives me nuts with it, is why they're jumping down and doing this part for the problem we did in the last section. And they didn't even ask about that, okay? They're just saying you can see the same results, and these results are, are compatible with each other, okay? Why they're doing that, I don't know, but it's fine, it's correct. Now, because the square bounded by 0 to x between 0 and 1 and y between 0 and 1 has an area of 1. There's a 1 by 1 squared. You can conclude the area shown under here is 2/3, and the area up here is 1/3. Okay? And your calculation had already told you that was 2/3. Now they're going back and saying, hey, yeah, it is 2/3. So I don't know why they stuck that other one in there. Now this agrees with the limit found in example 1, even though that example used a partition having subintervals of unequal width. The reason this partition gave the proper area is that as n increases, the width of the largest subinterval approaches 0. Okay? As n increases, the width of the largest subinterval goes to 0. This is a key feature of development of definite intervals. Now, it's kind of lost on me why they make such a big deal about it, but it's absolutely true, but I don't see what a big deal they do. In the definition of a Riemann sum below, know that the function f has no restrictions other than being defined on the interval a to b. Remember before we said it had to be continuous. Remember before we said it had to be always positive. This doesn't have those restrictions on it. The f be defined on the closed interval a to b. Let del, that's a delta, that's a partition of a to b, and all that's required here is the x of 0 be a, and the x of n be b, and that each of these is less than the one before it, after it, okay? That's all. You don't have to have a certain width or anything else. Where delta x of I is the width of the I subinterval from x of I minus 1 to x of I. That's that width. And C is any point. It doesn't have to be the midpoint, right point, left point, any point on the subinterval, just like we got to before. Then the sum, this is the same sum we did before, f of c sub I times delta x of I, where this is any one of those intervals, okay? That's called a Riemann sum. Now, the difference being the f, there's no restrictions, and the delta I can vary. But who cares? Because if you take the limit as n goes to infinity, even the largest interval is going to go to 0, okay? So it really doesn't matter. The partition delta here is whatever partition you want to make it. Okay, and it doesn't really matter. Okay, the width of the largest subinterval of the partition delta is the norm of the partition, denoted by the magnitude. That's what double lines is, the magnitude of delta. If every subinterval is of equal length, then the partition is called the regular partition, and the norm is exactly what we did before, b minus a over n. That's a regular partition. But it doesn't have to be. The general partition means, for a general partition, the norm is related to the number of subintervals of a to b, and in the following way, that b minus a over the magnitude of the largest subinterval, that's less than or equal to your n. So they kind of flipped them around and moved this down here and this up here, okay? But only made that a less than or equal to now, because they don't all have to be the same size. But this is going to be the biggest. The ends the smallest, because that's the largest partition. Okay. And in the long run, none of it really seems to matter at all, but they make a big deal about it. So the number of subintervals in a partition approaches infinity as the norm of the partition approaches zero. Of course, the more partitions you have, then even the largest one has to get closer and closer to zero. Okay? So the norm is approaching zero as it goes to infinity. That's all that matters. The converse of the statement is not true, though. For example, let n delta n be the partition of the interval 1 to 0 given by this, okay, where your partition here is 1 over 2 to the nth, where n can be any large number you want to. So that can be incredibly tiny, less than 1 to the n over 2 to the n minus 1 of the 1 over 8, 1 over 4, 1/2, and 1. Well, guess what? This one, the largest partition, no matter how big n gets, this one's the largest partition is still 1/2. So you can't go the other way, but when you go this way, it's true. You can't say that just because as n goes to infinity, that's going to force your largest partition to go to 0. It doesn't. Okay. So don't try to do that. This is what we're going to be dealing with, and that's really all that matters. As shown in figure 520, that's, where is it? Oh, there it is. It's at the bottom. Oh, here it is, right here. Okay. Shown in figure, 420. For any positive value n, the norm of the partition is 1/2. The largest is 1/2. This is back talking about the other one. And that doesn't approach 0 as n goes to infinity. These get smaller and smaller and smaller. That one stays 1/2. So that one doesn't do. Why they took up time for this here, I don't know. It really doesn't matter in what we're going to be doing. But we're through, not quite, but basically with Riemann sums. Okay? Now we're going to move to definite integrals. Man, believe it or not, you've been wanting to get here. You may not realize it, but you have been. To define the definite integral, consider this limit. The limit is that norm, that largest partition is approaching 0, of the summation of I equal 1 to n of alpha c sub I delta x of I. If that limit exists, consider that limit. To say that limit exists means there exists a real number L such that for each epsilon greater than 0, there is a delta greater than 0, such that for every partition with delta, the norm of that partition being less than that delta, it follows that the absolute value of the difference between L and this thing here is less than epsilon. Regardless of the choice C sub I, regardless of the choice of your partition, where the ith subinterval of each partition, delta. Okay? The delta just has to be less than, okay, I hate this. This is capital delta, that's lowercase delta. So this is partition of capital delta less than little delta. Seems like they could have used a different word, okay, or a different letter, but they didn't. All right. So here's your definition of a definite interval. F is defined on the closed interval A to B. We've always done that. The limit, all it has is defined. It doesn't have to be positive. It doesn't have to be continuous. It just has to be defined. And the limit of the Riemann sums over the partition delta, okay, and that's the partition such that the norm of delta is the biggest one of those partitions. As that biggest partition is approaching 0, then the sum, just like we've seen before, I equal 1 to n of alpha c sub I times delta x of I exists. This thing is going to exist if alpha is defined, and the limit of the Riemann partitions, if there is a limit, exists. Okay? Then alpha is said to be integrable on A to B and the limit is denoted by this thing here that we've been dealing with now for 2 sections. And they've been such a pain in the neck to calculate if you deal with the i's in there, okay, and the L sub i's and the delta i's and get them all in terms of i's. Do away with that. Make it the definite integral of f of x dx. Now the only thing new here is these 2 limits, okay? We're going to get into what those are in a minute, okay? But that's what we have here. The limit is called the definite integral of f from a to b. Number a is the lower limit of the integration, and the number b is the upper limit of the integration. So everything's just like before when we call this an antiderivative or indefinite integral. Now that if we put the numbers there, that means the a is going to be the first end of the partition, the lower limit, and the b is going to be the upper limit. Okay. Now, the Riemann sums were defined for functions with very few restrictions. A sufficient condition for a function f to be integrable on a to b is that it is continuous on a to b. So we jump back. We originally said it had to be continuous and had to be positive. They said, well, any integral will work on the Riemann sum. Now we go back and say it has to be continuous. We don't say it has to be positive, but it has to be continuous. So continuity implies integrability. Tough word to say. If a function f is continuous on some closed interval a to b, then it is integrable on the a to b. That is, the integral from a to b of f of x dx exists. Now, let me back up one more time here. Notice what's happened here. The summation sign, well, a combination of summation sign and the limit. The summation sign changed to an integral. So this was the Greek capital S for summation. That's almost like an English S, only a very small top and bottom. Okay? I is equal to 1 represented the A value. I is equal to N represented the N value, the B. Remember, x of 0 was A and x of N was B. And then your f sub c, that just becomes your f of x, your delta x becomes your dx. So it's a lot like the differentiation process by your limit becoming a delta x over delta y, delta y over delta x being dx dy. Now the summation becomes your integral f of x dx. Okay. So let's do this. Are we almost out of time? All right, sorry about this. We got through the hard part, the easy part is coming. Okay? So we'll start with example 2 next time. We barely got enough done to do an example now, but let's see. I think you can do 3. It's at both Calc Chat and Calc, whatever the other one's called. Goodness gracious. View, Calc View, okay. Hold off doing the definite integrals. We'll do those next time. So, example 3, exercise 3 is the only one. Good deal. I'm sorry? Oh, I see. Okay. Thank you. All right, here they come. More the merrier.
Do you have test 2?
What's that?
Do you have test 2?
What about test 2?
Do you have it? Do you have it with you?
Yeah.
I never saw my grade.
Oh, you just want to see your grade. Okay, I was going to say I can't return them because not everybody's turned them in yet.
Do I just slide my stuff under your door? Or?
That'll be fine.
Okay.
That's what I said last time. Yeah. Okay. There you go. Oh, man.
Is it 85 or
95.
95.
Yeah. Too bad. All right, good deal.
Thank you.
On the first one, I thought it was going to be less, but I found on your scratch work you had it right there. You just copied it wrong. But the last, or next to the last one, you just left off a term and a variable. So, but all the rest of it was right, so I gave you partial credit on it.
All right.
All righty.